this one, it says sketch the graph. This is going to be a review of what we've been doing over the last couple of classes, which is using that shortcut of DAB-C to graph any sinusoid. So again, I would look at this, and as a starting point, look at where I put my axes. I put it super low because I know that with a D value of 13.7, so if I make this my 13.7, that will be my sinusoidal axis. I'm going to have to go up and down 4.5. So up 4.5 will get me to 18.2, down 4.5 will get me to 9.2. And I try to set up my scale so that this is approximately to scale. Like if this is 13, then about a third of this is 4.5-ish. So it seems to be approximately to scale as best as possible. Anyways, we've already done the key, and we use the amplitude to label our max and min. So you'll often do both of those things together. Now your B value is 0.16 pi, so that means your period is going to be 0 divided by 0.16 pi. And you type that into your calculator. And you get 12.5. So I go somewhere on my x-axis and label 12.5. And divide that into 4 equal sections. So half of 12.5 is 6.25, half of that, 3.125, and then this would be 9.375. So we always find our period divided into 4 equal sections. That is our B value. Then the dash says graph it before the shift, but notice this one doesn't have a shift at all. So technically we don't have to do the dash in this situation because when we draw the graph, we're going to be done because there's no shift. So this is a negative coast graph. A coast graph normally starts at a maximum. This graph is going to start at a minimum because it's a negative coast graph. Then minimum, next sticky mark center line, next sticky mark maximum, then center line, then minimum, and we are able to sketch the graph. Now part B to this question, and I'll just read it first and then I'll come back to the graph. So part B to this question says that a bulk carrier, which is like a large ship, needs at least 14.5 meters of water in order to come into the dock safely. So when the tides go out, it can't come in because it'll hit the bottom of the ocean or whatever of the bay. For how many hours per cycle can it come in and be safe? So if we look at the graph, and we look at this graphically, it needs 14.5, so I'm going to put 14.5 on here. And with the blue dotted line, I'm just going to draw a horizontal line at 14.5. Does it make sense that only in this highlighted yellow section is the water deeper than 14.5? So what we're trying to figure out are the times that this is fine. So I want to go from this point, somewhere here, to this point, there, and figure out what those two values are. And we're going to do this in 2 ways, okay? We're going to do this first with technology. So some of you have graphing calculators. we're going to be able to do this with a graphing calculator. If you don't have a graphing calculator, then you'll need to go to an online program that allows you to graph, and I would recommend the following app. At home, you can put it on your phone. It is a great graphing calculator app. It's also something that you can use on any computer. So I'll show you what Desmos looks like as well. So first of all, I'll show you, if you were solving this with your graphing calculator, you take out your graphing calculator, and this will be really important for those of you taking AP Calculus next year, how to learn to use your graphing calculator, because you're going to be using it a fair bit in that course. And so on your graphing calculator, in the top left-hand corner, you have y equals. This lets you type in things into your graph. So I'm going to clear out what I have in here, and I'm going to start by typing in negative 4.5 cos 0.16 pi, and then I have to use the variable x, which is right there beside your alpha button. Close that bracket, plus 13.7. Okay. Now, if I hit graph right now, I want to see this graph. In fact, I kind of want to see exactly the graph that I drew by hand. But when I hit graph, I'm just curious what happens. I don't see my graph very much at all. In fact, probably if you're trying this, this is probably the graph you saw. Now, you have a little screen on your calculator, and you see what's in that screen, okay? If you want to, right, you could make your screen right here, and you would officially see nothing. Can you see if my screen was right there? I would see nothing whatsoever. Currently, my screen looks like it's like this. I saw that little bit right there, right? If I go back to my graphing calculator, I see just that little bit. So I have to use my graphing by hand to help me see it on my calculator. So we do that. Beside the y equals is the window. And when looking at the window, I don't really need to see the negative 10. Maybe I'll just start for my x minimum at negative 1. But I want to see at least a 12.5. So maybe I'll look a little bit further. Maybe I'll go up to 15. So we can set our scale along our x-axis. In fact, I can even, the x scale, that's what XSCL stands for, x scale. Notice how our ticky marks are at 3.125 each? I can make them 3.125, and those marks will show up exactly as I have them there. For my y minimum, I don't need to see negatives, but maybe I want to see a negative 1 because then it will at least draw my x-axis, okay? My maximum that we went up to was 18.2, so 10 wasn't enough. I'll go up to 20. And maybe I'll just set a y scale by 5s, because there's not going to be nice ways to make it exactly as we see it there. Now when I hit graph, it matches up perfectly to what I drew by hand. In particular, I want to find out when this graph hits the 14.5, so I can go back to y equals, and in y2, I can type in 14.5. If I graph that, now there's going to be a red line at 14.5, and here is the highlighted part. The very nice thing about technology is it lets you solve for where these two graphs intersect. On a graphing calculator, almost everything you want to solve on a graph is done above the trace button where it says calculate. So when I push the second button and the trace button, it gets me to the menu of things I can calculate. I can calculate any value I want. I can calculate x-intercept with zeros, where a graph is at a minimum, where a graph is at a maximum, and what I want to find out is where two graphs intersect. So I go down to number 5, or push number 5, push enter, and it says, which is your first curve? Well, I'm on the blue one, that sounds good. Which is your second curve? Well, and now it automatically goes to my second one, which is the red one, which is good. Would you like to guess? Not really. You can, like, I think it's going to go to this one. And you push enter on the guess, and sure enough, it finds one. It's at x equals 9.019. So I'm going to just write that on here. This point right here is 9.019. And I can find the other one the same way. So I go second, calculate, second, calculate, intersect. Now the calculator will always find the intersect whichever your cursor is closest to. So right now it would find the same one, so I'm going to use these arrow keys and slowly move it over. Now technically, can you see now I'm closer to the other one? That would be far enough. Some people like to be like, I like to get really close. Push enter, jumps to the second one, push enter, asks you to guess, push enter again, and we got 3.481. So we would be able to say for how many hours if we take 9 point, I forget what the numbers were, 9.019 minus 3.481. And take out our calculator. 9.019 minus 3.481. We get 5.538. Now we can still do this even if we don't have a graphing calculator. I'll show you what that Desmos program looks like. So you type in Desmos, and in Desmos on the left you can just start typing. So I'm going to type in -4.5 cos, put a brackets, 0, was it -0? Or was it positive? Positive 0.16 pi, and you can just write pi. Look at how I just typed in pi and it automatically changed it to pi. It's very intuitive. And then I'll put an x, close my bracket, plus 13.7. Okay? And just like your other graph, I can't see it anymore, but on Desmos you can like scroll in and scroll out. A little bit more intuitive because it's sort of used to how you're used to doing things on your phone and stuff like that. So you can move it around. And then in the second one, I can put y equals 14.5. Perfect. And the nice thing about Desmos is that if you want to find where they intersect, it's sort of like, oh, there's the point I want to find. Oh, here's another one. You just have to scroll over your mouse and just click, and we get the 3.481 and the 9.019 there. So obviously an online computer program, Desmos is a little bit more advanced even than your graphing calculator. But of course, calculators are what are allowed on tests because apparently there's things on computers like AI and all sorts of internet, like Google, and apparently that could help you on tests if you had access to that. I'm not sure how. Anyways, so that's unfortunately why you couldn't use Desmos on a test, but they both do the same thing. So we solved this with technology. Now, when you get to university, they're going to be like, no, you can't use any technology. You have to solve this by hand for a university class. So what I'm going to do is I am going to show you how to solve this by hand, but not fast enough that you can write it down. So don't even bother writing it down. Just watch. It'll be on the video. If later you want to rewatch the video and see it, we can go through that idea. But algebraically, if you wanted to solve this question, you would have to plug in the 14.5 for the y, because you know that depth. And by plugging that in, now you have an equation where the only thing you want to find is t. So we can solve for t using our algebra skills and our trig skills. And I'm going to tell you it's a little bit advanced. Like, first of all, can you see that it would be strategic to get the cos by itself? Because that's normally how we solve trig equations. So I move the 13.7 over, divide by negative 4.5, and now I get the cos by itself. But inside the cos, we have more stuff than we're used to. Because we're used to solving cos questions that say cos theta equals blah, blah, blah. And then you have to ask, is this on my pie plate? Can I do it without a calculator? Or do I need my calculator to find the reference angle? Now, 0.8 divided by negative 4.5 is not on your pie plate. So we're going to need a calculator. Also, with this value here being a little bit awkward, we can do something in math that's very strategic. If something's awkward, make it go away temporarily. And you can do that by saying, I'm going to just let theta equal all of that crap on the inside. Okay? Because then my equation looks nice. I'm like, this I feel comfortable solving. Well, how do I solve that? Well, I can find my reference angle by doing cos inverse, right? And we always find a reference angle with the inverse of a positive value. So I get my reference angle, and then I can say, oh, cos is negative, so according to my cast rule, I should look in quadrants 2 and quadrants 3. And so now I have an answer for theta. Theta is 1.75 and 4.53. Perfect. I can now go and substitute back and say, well, what was theta? Theta was this crap, 0.16 pi t. But now that I solve for theta, I can plug that back in and it'd be like, oh, well, now it's not hard to solve for t. I would just have to divide by 0.16 pi, and look what we get, our 3.48. Do the same thing with the other value, and we get our 9.019 or 9.02. So we get the same values algebraically. We could solve it that way as well. Okay, so as far as word problems go, I would consider this one the easiest word problem you will get, because it's not really a word problem, because they gave you the equation in the, we had all of the information we needed right away to solve this. Where things get a little bit more complicated with word problems is when they don't give you the equation, they just give you the situation. Yes, question.
For a question like that, if it wasn't a test, does the algebra count as marks or algebra does not count as marks?
Would the, sorry, what part?
In that question, would the algebra count as marks or not count as marks?
A lot of it would, like the reference angles and stuff like that. Although I would say on your exam, usually you don't see this level of difficulty. You will see that level once you get into AP Calculus or university. So you sort of prepping you for that, but they'll give you much nice, like chances are if they put something not nice inside of cos, usually their level of not nice is like just, how about just a 2t? Like something simple, okay? So the next situation we have is we're given a situation of something that rotates in a circle or something that's periodic in nature. So because it rotates in a circle, you know that it can be graphed with sine and cosine. And we have a Ferris wheel with a radius of 15 meters that rotates once every 20 seconds. So what does that mean for us? Well, I'm going to draw a picture. I don't know if you know what Ferris wheels are, but they're this ride where it has little chairs going around, and I guess technically it has to be connected. There we go. You got chairs going around, so you have someone who's very happy. Here we go. Unbelievable. I lost it. I used to have on my creative pen a happy face. That's so sad. I've got stars. What's this one? I do have that. There we go. There's my guy. All right, here's super happy guy. There we go. We'll get him on a chair. There he is. He's going on the Ferris wheel. Going to go all around. And we want to graph this. So first of all, right beside my Ferris wheel, I'm going to draw a graph. And on this graph, I'm going to have this part as height. And this part down here as my time. And I'm going to use what's written in the question to sort of develop my graph. Because they give me certain pieces of information. Okay? Ferris wheel has a radius of 15. So that means that from the center, straight down to the circle, that's going to be 15. Does it make sense that your diameter then is 30? Okay? It rotates once every 20 seconds. Passengers start at the bottom. This is normal for a Ferris wheel. They don't catapult you to the top when you get on. So here, Mr. Happy Guy, at the very start, at time 0, would it make sense that he'd be right at the bottom? That's the first point we can draw. I can mark it on here. At 1 meter, I'm going to be at the bottom at time 0. If it rotates every 20 seconds, does it make sense that at 20 seconds, I'm back at the bottom? How long to get to the top? 10 seconds. And can you see that we're starting to split this up into 4 equal sections? And at 10 sections, you would be right at the top, which is right here. How high is that? What number could I put as my maximum? Well, 31, right? Because we figured out the diameter was 30. The radius was 15. In fact, we can put our center value in at 16 and add our sinusoidal axes. And when will it be? At 5 seconds and 15 seconds, that's when we're going to be in the middle. So he gets on the ride. There he is. Right? Oh. There we go. Gets on the ride. 5 seconds later is there. At 10 seconds at the top, really scary, right? And then 15 seconds and 20 seconds all the way around. Ferris wheels are usually not very scary unless you don't like heights. We could make this question very scary by adding just one letter. Are you ready for this? Are you ready to make this scary? Okay. We're going to add the letter K. Holy cow. I don't know if you can imagine this. This is a huge Ferris wheel. It has a diameter of 30 kilometers. I think you would actually physically die on this Ferris wheel. We could figure out how fast we're actually traveling, but this would mean you would travel, here, let's get rid of that 50, you would travel in 10 seconds up to the top which is 30 kilometers high. This would be terrifying. How fast you would go. Definitely, I don't know. I don't even know if a seatbelt would help you. You would just be terribly, terribly scared, right? I mean, we could change seconds to hours, and maybe it wouldn't be so bad. It would be like the longest Ferris wheel ride in your life. Well, yes, it would. I told my class last semester a story. In my hometown, they have a fair every year in August. And they have 2 rides at the fair. And they are the same rides at the fair that they had when I was a kid. The same Ferris wheel has been there for like, I don't even know how much earlier than I was there, but years and years and years. And so since the same Ferris wheel is there all the time, it's not so exciting for the people in the town to be like, ooh, the old rickety Ferris wheel. So there I am, this is about maybe 10 years ago. I'm there with my family, and I'm like, oh, there's the Ferris wheel that I went on when I was a kid. I'll take you on it. And if you love Ferris wheels, you should make a road trip, because this is the best bang for your buck Ferris wheel you can get anywhere. No lineup at all. Only $1 a ticket. And since there's no lineup, when you get on, you go up to the top, like, ooh, come back down to the bottom. Go up to the top, ooh, come back down to the bottom. And after about 15 times, you're like, would somebody else please get in line? We would like to get off. But they're like, you can ride it for hours because there's nobody in line, and it just make you go around and around and around. So if you like Ferris wheels, that is a good deal. Oh, the other ride is a one where you sit in a chair and it goes around and your swing goes out to the side. Kind of, because you start straight up and down with chains, right? But as it goes faster and faster, you start going sideways.
In a Ferris wheel?
No, it's the second ride. My town has 2 rides. They have the Ferris wheel, and then they have this one where you go out, whips you around and around, and the chairs go out to the side. And so it's a little bit more exciting. However, as my cousin found out, he decided to go on the ride when he had a little bit of the flu. And if you're going very fast around and around in a circle, and you happen to have projectile vomit, yeah, it goes out for a moment, and then you fly right back into it. And that happened to my cousin when he was there. I also would have been like, isn't that kind of scary to be a person behind? So like, I don't know if you can dodge on those things, I'm not sure. Anyways, so what we have now is we have from our situation enough to draw one period of our graph, and if we have our graph, well then we can go dab C, maybe I'll write it this way. We can go dab C, put the dash in and everything. The dash is kind of helpful here too. Can we see our center line? Absolutely. Our center line is 16. Our amplitude, our A value, is the distance from our center line to a maximum or from our center line to a minimum. What distance is this or this? That's exactly the radius of our Ferris wheel, so that will be 15. Our B value is 2 pi over our period. It takes 20 seconds to go all the way around. So our B value is 2 pi over 20. Yes, you can reduce that to pi over 10, but I actually like to leave it as 2 pi over 20 because then the period shows up in my formula. I can see the 20 on the bottom, and I'm like, oh yeah, that was the period of my function. Kind of helpful that way. And now I'm going to start writing it, because I think in part, where does it say? First it says graph this function and find its inequation. So we're going to find this equation. In fact, we're going to find multiple equations. I did the dab part, and I'm going to leave the dash. The dash sort of says leave C to the end. So if my A value is 15, I'd have 15. If I choose sine, my B value is 2 pi over 20. X, I'm going to leave a space for C. And then my D value is plus 16. So there's the D and the A and the B, the dab part, is on there already. If I do a sine graph, you have to ask yourself, where does a sine graph normally start? In the middle, going up. So I'm going to do this in purple. I'm going to say, can I find a place where it's in the middle? Yes. Going up? Yes, right there. Where is that? 5 to the right. How do I show 5 to the right? Minus 5. Okay, let's do another one. Let's say you chose a cos graph. 2 pi over 20. So the D, the A, and the B doesn't change, right? If it's a sine or a cosine graph, your center line, your sinusoidal axis is the same. Your amplitude is the same. How long does it take to repeat itself? Is the same. The only thing that changes is that C value. And we'll do this one in orange. Where does a cos graph normally start? At a maximum. Can I find a maximum? Yes, right here. That maximum is 10 units to the right. So how do I show a shift of 10 to the right? Minus 10. So we've already got 2 graphs. I'm going to do one more because it's probably the one that's used the most in this situation. It's a cos graph. And it's a cos graph that starts at a minimum. So I'm going to do this point in green. And the reason this is used the most, so if it's starting at a minimum, does it make sense that I need a negative out front? But the nice thing about starting at a minimum is then there's no shift. So then you just can, that's probably the simplest equation, okay? Some people that say, oh, I don't like starting with a negative out in front, it confuses me. But in this case, when you're starting at a minimum, it makes sense to use a negative cos graph. So sometimes on the exam, they'll say, can you write an equation, right? Can you write an equation with sine and with cosine? And then once you have that equation, we can answer some questions. So we're going to answer some questions both using the graph and using technology. So first of all, if I went to 25 seconds and this kept on going forever, just like my hometown fair, right? 25 seconds, you'd be back to 16 again. And the question that is first asked of us is to estimate the height at 22 seconds. So on my graph, I can say I know that 22 is, I'll go purple again. 22 is right here. So if I go up to my graph, I get a point. If I was using my graph, I might say that that's at 3 or 4. Okay, it's an estimate. Okay, what's the problem with an estimate? Well, my graph scale wasn't the greatest. Maybe drawing, unless I draw things really accurately, going for my graph might give me an answer that's a little bit off. So how could we find the actual one? Well, I can put this into my graphing calculator or into Desmos, so I'm going to clear things out here. This time my graph was 15. Oh, I'm going to go with the easiest one. Negative 15 cos 2 pi divided by, oh, and if you have the newest calculator, you can even use your fraction button and write 2 pi divided by 20 x, close that bracket, plus your d value, which was 16. And again, I'm going to go to my window here, and now I want to see what I graphed. I already know that the period was 20, I'm going to go up to 25 to see a little bit more. My scale, I'm going to go by 5s. The maximum height we hit was 30, 31, so let's go up to 35. Now when I graph it, I can see this Ferris wheel ride. And if I want to find exactly where I was at 22 seconds, I can go calculate second trace button. This time I want to find a value. When x is 22, push enter. 3.86. Oh man, we got lucky with our guess. I guess technically you should always have 3 decimal places, 3.865. We'll practice going to 3 decimal places because that will be the expectation on all of your exams, unless they say otherwise. So if they don't say, they expect 3 decimal places. And if they don't say and you do 2 decimal places, they actually take marks off. I sort of disagree with that. Like, how hard is it for them just to say, there's only 5 calculator questions on your exam, and if you have to round, how hard is it to say on there, could you please round to 3 decimal places? And then if you screw up, it's on you, right? So like, it said it in the question. I feel like it's a little bit, like, you have enough to worry about on the exam. And like, oh, I also have to memorize that it needs to be to 3 decimal places if they don't say. Seems like a little bit over the top. Oh well. Okay. Next question says, estimate at what time you will be 20 meters above the ground. So we'll go to our graph. This time I'll do this on orange. 20 meters would be here. There's a spot there. There's another spot there. I mean, technically, there's many times that you'll be at 20 meters above the ground. Question? No, this one we're just going to use our calculator for now. Same thing with this one. Estimate what time you'll be at 20. So for an estimate, looks like maybe 6 seconds and 14 seconds. So here's our estimate. Six seconds and 14 seconds. If we want to do this with technology, we would have to go to Y2 and type in 20 to draw a horizontal line. And again, I can calculate where do these intersect, number 5, enter, enter, enter. 14.1. Oh, sorry, that's so close. Getting excited about our estimate. So this one was 14, I guess I need 3 decimal places. 14.141. And the first one, if I go back and calculate, the first one I need to move closer to that first one. I like to live a little bit on the edge. I think that seems to be close enough. If it all of a sudden goes back to the same one again, then all of that time will be wasted. We'll have to do it again. But I think it's close. Enter, enter, enter. Yes, 5.859. In a word problem, if there are units in the word problem, you need to have units in your answer. All right, so this question, a little bit more difficult because the equation wasn't given to us. We had to figure out the equation. Same thing in this last one. The world's highest tides occur in the Bay of Fundy. And tides come in and they go out, and they come in and they go out. And so anything that repeats itself over a certain amount of time makes a sinusoidal graph, either a sine graph or a cosine graph. So here we've got the data, and you've been hired to make the equation to figure out when the tides are coming in and out, so they can figure out, you know, ships coming in, what the water level is going to be, and what that looks like. So here's the dock, and we're going to draw a graph. We're going to put our depth here, and time here. If I write depth, does it make sense that a higher depth is deeper than a lower depth? Right? Some people sometimes would like to draw this so that this is your water level and have your graph below the axis so you can actually see depth. Right? Then you'd have negative values, but I'm just going to keep depth and say we have a maximum depth at 4:30 a.m. at 8 meters. So I'm going to put 8 meters right here as my maximum, but I'm not going to write 4:30 right here. This problem with time. How do you type 4:30 into your calculator? 4.5. Why 5? Isn't it a 3? Shouldn't you do 4.3? Wouldn't that be nicer? Yeah, like 4:30 is 4.5 because it's a half an hour, right? And you're like, oh yeah, 4.5. What are you going to do at 10:42? More than 10.5, but what are we going to do? Anyways, I'm going to draw this point, and then 6 hours, and 12 minutes later, so 6, that's going to be right here. 42, 10 point what? No. No. 10.7, right? So how do we figure that out? Well, how did you figure out 30? Did you just know that 30 out of 60 was a half? Right. But you should have still thought that you had a fraction, right? This is equal to half. 42 out of 60. Can you reduce that without a calculator? Yeah, you can divide both of them by 6. 7 out of 10. That's probably something you can change to a decimal, no problem. 10.7. And we have a minimum of 2 at 10.7. And this is the least amount of information that you need with a periodic graph to get everything. Okay? So we just have 2 points. From those 2 points, can you tell me where my center line is? Because we're going to have to get dab C out of this. Right? Extend it here. I'm going to write it off the side. Someone say 5? Genius. How'd they figure that out? It has to be right in between them, right? Some people take the maximum and the minimum and say, hey, this is just like my chemistry class. I got 8% on the first quiz, 2% on the second quiz. My average was 5%. Right? You can find the middle by doing an average. 8 plus 2 divided by 2. So there is my d-value. In fact, I can write that in right away. I know my d-value is 5. In fact, I also know, since I have my max and min, my amplitude is 3. From the maximum to the minimum, do you see that you have half of a period? You went up 6.2 hours. If you went up another 6.2 hours, you'd be back at a maximum. Does that make sense? What is our period? Because our b value is 2 pi over our period. And our period is how long it takes to go from maximum to maximum. Or you could go maximum to minimum and just double that. So if it goes 6.2 here, are you okay that my b value has to be 2 pi divided by 12.4?
How did you get that?
Because I know from here to here
What is
is 6.2. This means this will also be another 6.2, and that full period would be 12.4. In fact, I could split this into 4 equal sections, right? Add 3.1, 7.6, add 3.1, 13.8. And I could add those dots to my graph as well, and I have enough to draw my graph. And I've got the dab part, so I could write my equation. And I think the next question asks us to write our equations, right? Does it say 1 in sine and 1 in cosine or something like that? So let's start working. I know my a value is 3. Let's start with sine. I know that my b value is 2 pi over 12.4. I'm going to leave space for my c value, and my d value is plus 5. We'll go purple first. Where does a sine graph start? In the middle, going up. Do I have a point middle going up? Yes, right here. So how would I do that shift? It's to the right, so it's going to be minus 13.8. You could have also, there's one right here even closer. If you go back 3.1 to 1.4, you could use that number as well. Doesn't matter which number you use. Next, let's do a cos graph. See how I leave a space in case I decide I want to put a negative out in front? Because I could do a negative cos graph or a positive cos graph. The b value doesn't change. It's still 2 pi over 12.4. The d value stays plus 5. But a cos graph starts where? At a maximum. That maximum was 4.5 to the right, so I would write minus 4.5. So you were hired to find an equation. Now you can use this equation to figure out anything. Someone's like, I'm arriving tonight at 9:30 p.m. Will the water be deep enough for my boat? My boat goes 5 meters underwater. Well, you can just plug things in and say whether you're going to be fine or not.
But then might you have to like go really far into the future because you have to take this data on a specific day. So when you have to go like, okay, this is like 30 days past this.
Yes.
30 times 24.
You'd have to figure out, and then you would make also in your spreadsheet, you would probably have someone be able to just input their date and time, and then you would create the mathematics in the background to say, okay, that date and that time comes up to this number on my graph. And we go from there. Okay? So, some things that are interesting about real life. Real life doesn't usually work out nicely. Like here we have a 12.4 in our equation. That doesn't look as nice as before. Probably in real life, the 6.2 here that we figured out between the max and the min was already rounded. And if you round early and someone says, where will it be in 3 months? Chances are our calculations will be off. There has been historically tons of examples of mistakes that have happened for rounding early. Some of them catastrophic. I'm reading a book that was looking at rounding errors, and they found out that they had, the U.S. had an air defense system to protect one of their bases, and they made a rounding error something like to 45 decimal places is where the rounding error was, which usually didn't matter. However, they let the system run for a long enough time that the rounding error kept getting worse and worse. And there was a time that a missile was shot at this base, and their air defense shot in the air And because things are traveling so fast, if you're off by just decimal 0.00000000001, their air defense missed the missile, and the missile came in, hit the base, and a number of people were killed. And apparently, there was a memo that came out 2 weeks earlier warning, hey, there might be a rounding error to 25 decimal places. But if I tell you there's a rounding error to 25 decimal places for our map, you'd be like, yeah, who cares? That doesn't seem like it's very important. But sometimes little errors can be super, super important. So our technology, we can figure out equations, but real life gets messy, right? And right, wouldn't it be nice if these tides were perfect to be exactly 24 hours, just like our day is 24 hours? But technically our day is not exactly 24 hours. There's like, it's just a little bit off. We have all of these issues. Yeah.
You just set like the maximum at 0 and then do the shift so you don't start at like 4:30 in the morning.
You could, and then have 0 as a maximum. So you can do all of these kind of changes to make things work. Like, we have things in place. Even our regular years are kind of screwed up. What did we have this year? A leap year, an extra day. What the heck? Did you know? I think it's every 100 years they have to put in a leap hour. That's weird. The whole calendar is actually, like, it's pretty good right now, but over time has been really messed up. Like there was in the 1700s, France decided to get rid of 14 days in October. It's weird, eh? They're like, they were screwed up. They're like, this is not working anymore. They went from October 1st to October 15th. That would suck. I would have missed my birthday. And not even so long ago, in the early 1900s, 1908 Olympics, at that time, England was using a different calendar than Russia. And the Russian biathlon team came to the Olympics and arrived 2 weeks late and missed it.
Just the biathlon team?
I don't know. That's the only one that, sorry, I know of, just the biathlon team. I'm sure the rest of the team probably missed things too. But isn't it, like, that's not that long ago. Like, 100 years ago doesn't seem like it's that long ago. And for two calendars to be different in two different countries only 100 years ago, that's kind of weird. Anyways, let's finish up this question, and then I have some that I want you to try. So we've done our two equations already. Estimate the depth at 1:30 p.m. We have to think here, where does 1:30 p.m. fit on our graph? I don't have AM and PM anywhere. I'm going to label it in purple. What number should I look up? 13.5 would be 1:30, right? In Canada, we use 1:30. A lot of places around the world use a 24-hour clock. They would never talk about 1:30 p.m. They would always talk about 13:30, which, you know, for us is like, oh, that's weird for us. But then it makes it, you don't have to say AM and PM, right? So 1350. So if we estimated, I'm gonna say, oh, our estimates have been so good, I'm kind of nervous. I'm gonna go with 4. I'm gonna go with 4 again. So again, if we want to find the actual, we're going to need to go to our calculator and put in our values. So we had 3. Which one should I use? They're both basically the same. So I'll use the 4.5 with the toe strap. I like the max one. 3 goes. Get my fraction button out. Was that pretest?
Is it just some quizzes the kids had handed in.
Oh, okay.
None of mine handed in to you by any chance, no?
They would have put it in the bin, so I can check when
Yeah,
I'm through.
when you get a chance.
Yeah.
I'm missing a couple, but I might have misplaced them.
And then we have x minus 4.5. And then plus 5. So I've typed in my equation. I can hit graph. There it is. I didn't change my window, but it still shows up. So I'm okay with that right now. And I want to find, second, calculate the value at 13.5. 4.546. All right. I'm still happy with my estimate. And was there another one to estimate? No. That's it. Okay. So then I have 2 questions there at the bottom that you can do. I can also tell you that if you want more practice, from the textbook, you can do questions 3 to 9. You can ignore the questions that are written at the bottom. So there's 2 of them on your paper that you can try. And then in your textbook, you can do 3 to 9.
On what page?
This is in section 6.7, so that'll be on page 548.